Thank you so much for the introductions, and also a big thanks to the Breathing City network for inviting me to present today. As you said, I'm based at the Bartlett at UCL, at the Institute for Environmental Design and Engineering, and the work I'm going to present today is the result of an EPSRC funding project that looked at indoor environmental quality and synergies and conflicts with energy efficiency, climate resilience, and potential impacts on learning performance, and the development of a school building stock modeling framework. And just to say that, of course, this is what I'm going to present today is the result of collaborative work, and the names of my collaborators are there on that slide. So just a brief overview of what I'd like to cover today. Of course, it's a vast topic, and it's not possible to really do it justice within 40-45 minutes, but I'll try to do my best to present these very complex interrelationships and our methodological approach to address them. So I'll just give a brief introduction to what motivated this study, and just a very brief summary of established relationships of indoor environmental quality factors and impacts on learning performance and health for schools. And then I will go into a little bit more detail in terms of how we developed our school building stock archetypes for Britain, and the work we then did on indoor environmental quality modeling at the stock level. And then for the second part, I'm going to present some of the ongoing work that my colleagues at the London School of Hygiene and Tropical Medicine have been doing on health and cost impact assessment, and on the development of the kind of final output of this project, which is this multi-criteria decision analysis framework. So we'd just like to say that even though this project ended this summer, as it happens, we're still working on some of the final publications. So some of the parts towards the end are very much work in progress. So watch this space, because we have submitted 2 papers that are currently under review. So I won't be able to present those final parts just yet. So why do we think that looking at indoor environmental quality and the climate resilience of school buildings in the UK is of vital importance? Well, school children are estimated to spend around 30% of their life at school, in school environments, around 70% of which is inside a classroom. So the design, operation, and resilience of classroom settings is absolutely important, because poor indoor quality and exposure to high temperatures can have very negative effects on both the learning performance and the health and well-being of school children. So looking at the existing epidemiological and built environment literature, we can identify a number of established relationships between indoor environmental quality factors and health or well-being or learning performance outcomes. So, for example, in terms of air quality, children tend to breathe more air than adults compared to their body size, and therefore they're particularly vulnerable to a range of air pollutants, in particular traffic-related pollutants such as nitrous dioxide or particulate matter, and this can have acute adverse health and learning effects, such as, for example, respiratory irritation, asthma, and other effects, headaches, nausea, attention loss, that might affect their cognitive performance at school. There are also established relationships between low ventilation rates, high concentrations of carbon dioxide, as well as high temperatures, and with poor cognitive performance. And this is also important because children have a limited ability to thermoregulate compared to adults, and therefore, again, they're more prone to the adverse effects of overheating. In terms of the energy efficiency of the current school building stock, school buildings are responsible for around 15% of the country's public sector carbon emissions. And when we look at a school's budget,
do you want to send me what you've done?
A significant proportion is related to space heating and fuel costs. So this is what makes the largest proportion of energy use for schools. And this is, again, very important at times of, living crisis and increased fuel prices. And many argue that the school building stock offers significant opportunities for energy use savings and carbon emission reductions because a lot of the occupancy patterns, activities, and equipment use are relatively homogeneous and relatively easy to predict. Of course, there are other challenges such as the intermittent use of rooms and classrooms and other rooms. That might be a challenge for overheating mitigation. But in broad terms, the use of school buildings is relatively homogeneous. And of course, as we all know, climate change will pose unprecedented challenges to the built environment and our societies. And vulnerable individuals, such as younger people, are expected to be particularly affected. So we went through a 40 degrees heat wave this summer, and these were some of the headlines. A lot of discussion there about school closures, about schools adjusting their school uniforms or the way they operated during those 2 days of the heat wave. So schools and the school system is going to be affected by increasing temperatures. And what is really important to note is that energy efficiency strategies that lack a whole systems approach could potentially have unintended consequences for indoor environmental quality. So what does this mean? So as we're trying to increase the energy efficiency of our building envelopes in order to reduce our space heating needs and the associated carbon footprint of buildings, if we don't also think about the indoor environment, the concentration of indoor air pollutants, or the thermal comfort during the summer, this could lead to maladaptation. So as we make our building envelopes increasingly airtight and more thermally insulated, this could potentially lead to the concentration of the trapping of indoor air pollutants and heat indoors. Of course, if we don't incorporate appropriate ventilation means or other passive cooling strategies. So a systems thinking approach is really needed. And of course, it's really important to note that there are additional challenges for schools located in urban environments. On the one hand, we have the urban heat island effect, which is the effect of experiencing higher temperatures in urban environments compared to their rural counterparts. And this is likely to exacerbate indoor overheating effects in those urban schools. And at the same time, it has been noted that children living or attending schools near high traffic roads could potentially be exposed to much higher levels of traffic-related pollutants and possibly having higher incidence and prevalence of respiratory conditions such as childhood asthma and wheeze, etc. And of course, there is also a potential dimension of socioeconomic and health inequality there in terms of the relative exposures and associated health effects. So to address some of these challenges that I've just outlined, we developed this project. So the acronym is ASPIRE, standing for Advancing School Performance, Indoor Environmental Quality, Resilience and Education Outcomes. So this was a 2-year project funded by EPSRC, a collaboration between our research team at UCL and colleagues at the London School of Hygiene and Tropical Medicine. And we're very lucky to have a range of partners representing both the government as well as the construction industry with SIPSI and also other industry representatives who specialize in low energy school buildings. Healthy buildings in general. So even though it was a 2-year project, we were obviously, there's a lot of research projects affected by COVID and experienced several delays there. And we had a small 6-month extension to the original duration of the project. So the overarching aim of the project was to address this knowledge gap. Can school buildings achieve low carbon emissions whilst maintaining high indoor environmental quality that enhances both learning and health? And to address this, our aim was to create a toolkit for various stakeholders that could be used to assess the relative impact of a wide range of design operational strategies. And this overarching aim was translated into 5 objectives, each one of them linked to an individual work package. So the first step was to look at those established relationships in the relevant literature between classroom exposures to indoor air pollutants and temperatures, and school children's cognitive performance and health through a meta-analysis of existing literature and field data. The second step was to represent the variability of the UK school building stock by generating a series of school building archetypes that are broadly representative of the school building stock and suitable as inputs for building performance analysis. The third step was to use dynamic building performance modeling to quantify those exposures of UK school children to indoor air pollutants and high indoor temperatures under a wide range of retrofit scenarios and different operational behavioral strategies for a range of climate projections. The fourth step was to carry out a health impact and cost effectiveness analysis in order to calculate the impacts of those design retrofit operation strategies and climate change on a range of health and other outcomes and education attainment with a focus on childhood asthma. And the last step that we're still working on is this development of a multi-criteria assessment framework that allows stakeholders to compare the relative performance of all these scenarios and policy options. So this was the project structure. So as you can see, there's 5 objectives translated into individual work packages, all very closely interlinked, and mainly feeding the modeling work, feeding into the health impact and cost effectiveness analysis. And there's that element of translation there through stakeholder engagement and knowledge exchange with our excellent project advisory board into the MCDA, the multi-criteria decision analysis framework. And we hope they will eventually be able to inform policy and practice through these findings. So in terms of the existing literature in this area, those existing relationships, there is a very strong link between indoor CO2 concentrations and indoor temperature in classrooms and performance of schoolwork. So these are some graphs produced by Professor Bartlett. There is the reference there that show the relationship between CO2 concentration in ppm and relative speed of a specific test. And the one on the right shows the relationship between indoor temperature and relative performance, again in some sort of cognitive test. So we looked at this literature in a lot of detail, and this then fed into the translation of our modeling outputs into impacts on cognitive learning performance. Now, in terms of developing the school building stock archetypes, we just move to the next slide. We analyzed the Property Data Survey Program, PDSP database, which contains information about a range of variables describing the school building stock, including form, construction era, ventilation mode, whether it's naturally or mechanically ventilated. And you can see in these graphs there the distribution of schools in terms of whether primary or secondary across different regions, whether they're naturally or mechanically ventilated. And you can see there at the bottom left that the majority of schools in the UK are naturally ventilated, which I think is quite important because this means that during the summer they primarily rely on passive means for cooling. And also You can see there the distribution of primary and secondary school building stocks across the 5 construction years pre-1919, interwar 1945 to 66, and 67 to 76, and then more recently built stock post-1976, and then whether they're single or multi-block. So this then led to the development of our what we call our seed models, which represent those distinct areas within school building programs. So schools built within these areas often have similar construction characteristics, maintenance needs, and life cycle expectations. So they share a lot of common characteristics in terms of their building fabric and form. And this is how we modeled the classroom. So we had 5 construction eras, different locations represented by different weather files, and 4 orientations. And we developed models both for fixed ventilation scenarios, so providing a constant supply of, say, 8 liters per second per person, or natural ventilation that are weather dependent and driven by a weather file in our program. So a school building stock model was developed that quantifies the exposure of UK school children to indoor air pollutants and high indoor temperatures. So the seed models were combined with the PDSB database and generate the archetype model. So that variation of different geometries, building fabric characteristics, etc. And then this series of archetype iterations were simulated using the widely used and tested Energy Plus dynamic thermal modeling software, with the main outputs being temperature, humidity, ventilation rates, energy use for heating, and a range of pollutants including carbon dioxide, PM2.5, and NO2. I think it's important to note here that although we modeled indoor CO2, we only model externally generated, so traffic-related particulate matter and NO2. And future work could also look at additional internally generated pollutants such as VOCs and so on. And then there was a translation step I mentioned earlier. So post-processing outputs were essentially the main modeling outputs, but translated using those relationships that I mentioned earlier to translate, say, temperature in cognitive performance levels, overheating using the Building Bulletin 101, etc. And also carbon emissions were calculated using existing fuel intensity factors and so on. In terms of comparing our modeling outputs against the existing data, we compared our energy use outputs for English primary school stock data against measured data based on the Display Energy Certificate database for those schools. And we found that broadly there was good agreement for the naturally ventilated schools, as shown there in the graph. Less so for the mechanically ventilated schools, but our focus was very much on the naturally ventilated ones. And this is a follow-on paper that I think to date presents our work in sufficient detail. So Grassi et al. As part of a special issue for the Buildings and Cities Journal, assessed indoor overheating risk and air quality within an English classroom stock model. So we had 111 archetypes, and this was kind of the this complex diagram there shows the various combinations we simulated. So different terrains, 13 geographical locations, 5 construction eras, kind of an input of whether the building had been modified or whether we had the original building with no extensions, whether it was naturally or mechanically ventilated, and so on, different orientations. And then following this initial modeling work, we focused on 3 selected samples in terms of climate scenarios, energy retrofit scenarios. So we had a base case building fabric scenario and a retrofit case. And then on top of this, all possible combinations with a series of indoor environmental quality measures. And then we looked at performance metrics of overheating risk, space heating demand, and a range of pollutants. And the focus was very much on that conflict between overheating, air quality, and energy use. So just a little bit of technical detail there, just in case it's useful from that paper. So as you can see there was a variation across different construction eras and the way some of the construction building elements were composed in the model. So if you're familiar with Energy Plus, that might help understand a little bit what the modeling inputs were. And then this is the summary of the measures of the building fabric retrofit scenarios. So one retrofit measure included upgrade external wall insulation, so decreasing heat transfer through the building fabric, the addition of double glazed windows by assuming that all windows were replaced in all classrooms, and the addition of external shading through overhangs on every window. And then this summarizes the overheating mitigation / operation / behavioral scenarios. So these included additional ventilation through increased window opening, so modifying the angle of the window, the addition of curtains for internal shading. So as we know from existing modeling work and some monitoring work, internal curtains might not be as effective as external shading. They might have some effect, and also nighttime cooling by opening windows permitted. So these are some of the results of the study. So this graph there shows ventilation rate and internal temperatures during the warmest week for this weather file. So it's kind of a worst case scenario, west-facing London classroom for the 2020s climate for a range of different indoor environmental quality management and retrofit scenarios. So as you can see, some quite high temperatures are observed, but there is a significant reduction observed through the introduction of the retrofit strategies and the behavioral measures. And broadly, the peak occupied temperatures and the ventilation rates that we observed were consistent with those observed in the Symphony European project for West Europe classrooms. So this very busy table there summarizes some of these outputs. Just in summary, a range of retrofit and passive cooling measures were shown to be able to mitigate, I guess, overheating alone, probably by around the middle of the century. But it's likely that mechanically driven active cooling and filtration may be required towards the end of the century. And again, this is broadly in line with observations we've made in other similar studies on overheating in UK housing and other building types. And while no single measure predicted universally positive effects of building performance, we found that night ventilation and the addition of overhangs were particularly effective in terms of mitigating overheating across the school stock and across the different archetypes. And of course, a feasibility assessment is needed after that. This is very much a theoretical modeling exercise, and night ventilation might not always be possible, especially for urban schools or where there's security concerns. But you can see there very clearly that especially in terms of traffic-related pollutants entering indoors, the results there very clearly reflect the background regional levels of air pollution. And so this graph there, again, tries to summarize these outputs in a slightly different way. So as I said, we post-process those outputs in order to translate them into metrics that will then be input into the health impact analysis and the multi-criteria decision analysis framework. So these two kind of box plot graphs showed the variation of those metrics across different climate scenarios and also the variation by classroom orientation. So I think the first one is quite interesting. So what it shows is, so when the values move towards the right, this indicates improved performance in terms of those metrics. So what we see is that as we move towards the future, space heating needs are decreased because of a warming climate. PM2.5 concentrations are reduced, and there is a slightly similar in terms of NO2, and I think this possibly reflects the fact that there is additional window opening, additional levels of protection through the building fabric. There is an increased risk of overheating as a result of, again, a warming climate, which is also reflected in terms of potentially reduced cognitive performance. So moving on to the second part of the project. So this is the work carried out by colleagues of the London School of Hygiene and Tropical Medicine. So Dr. James Milner, Dr. Phyllis Caracas, and Dr. Zaid Jalabi. I'll do my best to describe it, but if there are any technical questions, I'd be very happy to direct any questions to my colleagues. So they carried out a detailed review of the evidence on air pollution-related health outcomes in school children. And following this, they developed methods to quantify the impact of low-carbon school design on health. And they focused this evaluation of health outcomes in the short term on asthma in particular. So they developed this morbidity impact model in terms of attributable asthma cases. So the input data were levels of NO2 in 2020 that we provided from Energy Plus. They use regional asthma incidence data from the Global Burden of Disease study and census data from the Office for National Statistics. And this kind of describes the various inputs that went into their calculations and the life table methods they used in more detail. So this assessment of the impact of school indoor pollution in UK schools on childhood asthma. So they estimated the burden of childhood asthma that may be attributable to indoor NO2 across various regions in the UK. And they assessed energy efficiency strategies regarding effects of asthma incidence in the future through the comparison of initially two scenarios of retrofit. One, which was base case, unretrofitted, and only looking at very ambitious levels of energy efficiency, such as EnerFit levels of retrofit. And in addition to this, they also carried out a cost effectiveness analysis that built on existing methods that they had used in previous work, including economic analysis performed for NICE, as well as the hiding model that they had developed for BASE. So these are some of those initial findings. So again, perhaps unsurprisingly, the highest indoor concentrations were estimated in the Thames Valley region, including London, in particular in older school buildings, possibly due to the leakier building envelopes that are likely to increase the ingress of external pollutants indoors, while the lowest concentrations were found in the new schools in Wales. And what they found was that improving energy efficiency, for example, by making the building fabric more airtight, more insulated, or through improved glazing, it increases the airtightness of those school building envelopes and reduces the air exchange with the outdoors, therefore reducing the amount of external pollution entering the school classroom. So what they found was that model asthma incidence cases were reduced as a result of energy efficiency measures. Of course, there's a caveat there in the sense that we didn't model internally generated pollutants. I think that's quite important. And again, future work could indeed look at those indoor-outdoor issues and those relevant exposures. So the last part in the project was the development of the multi-criteria decision analysis framework. So this was led by Zaid Jalabi and Phyllis Caracas, and as I said, it's very much ongoing work. So the MCDA framework, if people are not familiar with it, comprises the following elements. So 5 key components. The first is a set of policy options, and these are usually proposed by a number of experts. In our case, these were the members of our project advisory board. Then we have a set of criteria for assessing and comparing the options, a set of models to determine the impact of each policy option against each criterion. That was our modeling frame, the dynamic thermal modeling building stock model that we developed. And then we elicit weights that assign the relative importance of each criterion. And we did this through an online survey of stakeholders, of which the results I will present shortly. And finally, integrating the impacts and the weights to determine the overall value of each policy option across all criteria. And this final step is what helps us identify the optimum solutions, again, based on the preferences of the various stakeholders. So I think this little diagram there might make it a little bit clearer. So in terms of evidence, we seek expert opinion to identify which policy options and we should be looking at. And this is focused on research evidence on the impacts, and this could come from models, observations, or experts. So as I said, in our case, this came from a project advisory board. And then we have the weights, so the relative importance of the criteria. So this comes from the stakeholders, and all weights of the criteria add up to 1. So the weight of each criterion is between 0 and 1. And finally, this is the combined comparison of the performance of the different options. And so the intervention with the highest score is the best across all criteria. So in our case, it would be, for example, an option where we would have achieved the lowest carbon emissions, the lowest space heating needs, but at the same time achieving satisfactory levels of thermal comfort in winter, the lowest risk of overheating, and the lowest levels of exposure to indoor air contaminants. So unfortunately, due to COVID, we had to slightly change our study design. So this was supposed to be carried out in 2021 as a kind of face-to-face, or a series of face-to-face workshops where we would have invited a number of people representing different stakeholder groups to devote and provide those weights. So unfortunately, as you can imagine, this was not possible. So we had to carry out an online survey targeting different stakeholder groups, such as representatives of the government, local authorities, construction industry, school staff, so both teaching staff as well as other education professionals, and non-teaching school staff, and as well as school communities and parents. So through snowball sampling, we carried out this online survey last summer, and we had around 210 respondents, of which only 115 result in valid entries. But this shows their votes in terms of the importance of these 6 criteria we had. So those criteria were suggested by our project advisory board. And then the respondents of the survey were asked to rank them based on their importance. And of course, the sample might be quite small to be able to say something in terms of, its statistical significance, in terms of, the differences we observe. But I think what's really interesting is that the majority of the respondents voted pupil learning performance as the most important criterion. But then there were some, even though they're broadly similar in terms of the trends, there are some slight differences there. For example, I think it's quite interesting that the construction industry professionals seem to place more importance in terms of the school building carbon footprint, whereas the non-teaching school staff appear to prioritize a little bit more the cost savings due to the reductions in space heating needs and ventilation systems. But I think it's also worth noting that, again, this was carried out during a period of in between lockdowns where people were very concerned about COVID. So it's kind of a snapshot in time. And as I've discussed with my colleagues, this is perhaps one of the limitations of this approach, of the MCDA approach. So the next step now is to indeed use these and the translated outputs of our modeling framework and to try to identify what would be the optimum solutions based on those weights and those criteria. So again, based on what the stakeholders voted as being most important. And of course, this is a framework that we've developed that could possibly be used in the future with updated values, etc. So this is very much a work in progress. So as I said, we have two publications currently being prepared. One of them has been submitted and is currently under review. The other one is about to be submitted. That will be presenting this this final step of the project. So apologies, I'm not able to share this just yet, but please watch this space. So in terms of future work, the next step is obviously the completion of the MCDA framework. But future modelling work could look at the incorporation of additional retrofit and operation scenarios. For example, we looked at a series of fairly mainstream passive cooling strategies. We could also incorporate more advanced overheating mitigation technologies. Also COVID-related ventilation requirements. So when we started the project, when the project was conceived, it was kind of pre-COVID. So COVID related ventilation requirements have not been a specific focus of the work, but if there are new regulatory requirements, this is something that we could potentially incorporate in the framework because it's very modular in its nature. As I said earlier, a significant caveat is the lack of internally generated air pollutants. So we could possibly include VOCs or other pollutants. But also something that our research team is moving towards is going from archetype-based building stock models that have a lot of caveats and limitations in terms of representing the stock. So shifting to the development of one-by-one models where we're able to look at specific schools in a little bit more detail. So I'm not sure how I'm doing for time. I think we're okay. So thank you. And
you're fine. Yeah, you're doing very well for time.
Excellent. So these are our publications in case people would like to find out about the modeling work in particular in more detail. And yeah, thank you so much for listening. And any questions, yeah, feel free to drop me an email after the end of the webinar. And I think we can take some questions.
Great, thank you very much, Anna. That was absolutely fantastic. Really thorough, really robust piece of work. Yeah, so we do have some time for questions. If people do have questions, can you stick your hand up and I will look for you and call your name out. I'll keep an eye out for that. I've got one just while we're sort of waiting to see if there's any coming in. It was, and I may have missed this, so apologies if I have. It's to do with who operates the buildings in terms of controls and so on. So I mean, I've been aware from stuff we've done, which is that some buildings, particularly PFI things, are very much controlled by a third-party organisation, an FM, who have certain kind of employers requirements, and so some are much more, in a sense, hands-on and require direct intervention. Is that where might that be in terms of operation and response to different scenarios?
Yeah, this is really important. So we try to capture the views of, say, facilities managers or other non-teaching staff that might be responsible for the operation of school buildings through the survey. I can't quite remember the exact figures now. I think we had a decent sample. But yeah, that's where you would sit within the framework in terms of kind of them expressing it. And I thought it was quite interesting that the non-teaching staff as I said, place more importance in, the running costs of a school building, because they are the ones dealing with it, the ones being responsible for it. But of course, I think it's absolutely important to incorporate this into a greater level of detail. So I think more work needs to be done in this area in terms of the interface between the facilities manager, those third parties, as you said, and the end result of making those decisions on a daily basis.
Indeed. Okay. No, that's really helpful. I don't see any other hands. So I do have another question, which is I have to say slightly related. I mean, what there has been, for example, is greater use of CO2 sensors in classrooms. Some of that has come about through kind of COVID and
yes.
so on. And there has been work previously, which has looked at that. Might that be a factor in terms of control of indoor air quality? So one of the things is, obviously with the CO2 sensor, then that might give you a visual trigger of something which is otherwise imperceptible to occupants.
Yes, absolutely. So yeah, as you said, due to COVID, there has been increased use of CO2 monitors, and I think this is a really important step in terms of informing, occupant decisions in terms of window operation, etc. And I think in the overheating field, there have been requests for a while to have temperature sensors as well in most classrooms, because again, people are slightly better at judging overheating, but again, we're not great at necessarily assessing temperature. So I really see this as a very positive step. And of course, the issue there, the conflict is that in the relationship between indoor CO2 that might, high concentrations of which might have a very negative impact on students' ability to concentrate and do schoolwork, and the ingress of externally traffic-related pollutants. So we have that inverse relationship almost, which is, I think, it is reflecting a lot of our modelling results. And it's that optimization exercise, or potentially looking at other solutions such as, filtration or smart controls, etc.
Yeah, no, that is interesting, because I was struck by one of the conclusions was that it was describing things like increased air tightness as a protection against outdoor pollutants.
Yes, that was a very interesting result for me as well, because I think we see energy efficiency measures as the potential risk of trapping pollutants indoors, because we tend to think about, especially in housing, we tend to think about those internally generated pollutants that come from furnishings or cleaning, personal hygiene products. But I think in some areas, externally pollutants might be more dominant in terms of overall emissions. So that's why I think one of the key pathways in terms of this project would be to look at the wider range of pollutants.
Yeah, no, that is interesting. Obviously there would be a lot of localism there in terms of what those, and I suppose those things would change over time as well if we're getting changes in the generation. If we move to electric cars and
exactly.
stuff like that may change.
Yeah.
Right, I don't see any hands, so I'm going to just do one more question. It is okay. With the changing climate, will adaptive comfort become more of a thing in terms of judging overheating as we become more used to a warmer climate? Is our threshold for overheating going to shift?
Yeah, so there is a lot of research by epidemiologists and other colleagues looking at those potentially changing acclimatization levels of populations in currently heating-dominated climates, such as the UK. And as you say, it's very likely that we will be, in the future, will be much better adapted to a warmer climate. So I come from Greece, where schools would have closed in probably mid-June, and then reopen mid-September. So there are different ways in which schools could be adapted to a warmer climate. I think an obvious one this summer was the adjustment of the school uniform rules. In some schools, they said just come with, in whichever way you feel more comfortable. But other more, subtler, shall we say, behavioral adaptations to warmer weather, which might happen perhaps, more gradually. And then, at a kind of population level, you see those shifts that are translated into, slightly higher heat-related mortality and morbidity thresholds.
Okay, grand. I'm not seeing any hands up. There's one comment which you may not have seen from Victoria Beale, just sort of pointing towards the data set from SAMI, which may be useful.
Fantastic. Thanks, Victoria. We'll be in touch. That sounds really, really interesting. Great
stuff. Okay, fine. Well, if there are no questions or no further questions, then we'll probably draw it to a close. So, Anna, thank you very much. Really interesting project. There's actually quite a lot of stuff I could ask you about it, but I won't monopolize it. Really interesting. Thank you for your talk. It's been recorded, so it'll be available later if anybody wants to pick up on it. Yeah, fantastic. Thank you very much, and thank you everybody for attending. And I hope you enjoyed it. And I'm not sure when the next one is, but it'll be on the Breathing City website. So thank you very much.
Thanks again so much for inviting, and to everyone for attending.
Brilliant. Thank you.
Thank you.